Guys, how's it going? Mike coming back at you with another video on number theory. In the previous video, we saw a couple sample problems showing us how we find the number of positive divisors of a given positive integer n, as well as the sum of those positive divisors. We saw the formulas. We use the formulas after we put our number in canonical form. In this video, I just wanted to do a little bit of a side venture, but it does have applications to number theory. I want to talk about the greatest integer function as well as what is its use in number theory. So this next function is not a number theoretic function. So for an arbitrary real number x, we denote as, so we have x and then inside of square brackets, we denote this thing to be the largest whole number that is less than or equal to x. That is to say, open square bracket x and then closed square bracket is the unique integer that satisfies the following inequality. So yeah, that is your inequality right there. So case in point, the greatest integer that is less than or equal to 2.5 is going to be 2. The greatest whole number that is less than or equal to pi, which is 3.14, obviously is going to be 3. The greatest positive integer that's less than or equal to 10, well, 10 is already a whole number, so the greatest whole number that's less than or equal to 10, that or equal to part kicks in, is 10. And then when you have numbers that are negative, that's where it kind of trips people up just a little bit. If you have minus 2.71, the greatest integer that's less than or equal to negative 2.71 is going to be minus 3. People would be tempted to think that the answer is minus 2, but that would be greater than or equal to the given x value here, and we want the largest integer that's less than or equal to. This is also called the floor function, and there are multiple ways that you could see that written out, but for our purposes here, we're just going to look at it in this one particular way. And now we come to the use of this function in number theory. This function can be used to tell us the highest power of a prime p that will divide n factorial. And the following theorem or fact gives us a relatively easy way to find what that power is. So if you have a natural number n, just a positive whole number, and if p is a prime, then the exponent of the highest power of p that divides n factorial, basically just the highest power of p that will divide n factorial, is given by an infinite sum. K starts at 1 and goes to positive infinity of the floor of n divided by p to the k. Now, the formula says that the sum is not finite. However, in reality, this actually is a finite sum. And the reason why that is because you have a fixed value for n, you have your prime p, and then you're raising your k value. You're raising the power on that prime p. And for a fixed positive n value, at some point, the bottom, the p to the k, is going to be greater than n. So you'll be taking the quotient of two positive numbers, but the number on the bottom is larger than the bottom on the top. That's always going to get you something between 0 and 1. And if you take the floor or the the largest integer that is less than or equal to something between 0 and 1, you're always going to get 0. So once you hit that point, you just end your sum there, because any terms after that are just going to give you zeros. So while the formula states that the sum is not finite, in reality, your sum is indeed finite. So I have a practice problem here written inside of my notes. It's pretty straightforward to see how this gets worked. What is the highest power of 2 that divides 40 factorial? So here, 40 is our n value. 2 is our prime. So we're going to substitute these values into our formula, and we're going to see what this highest power is. So I'm going to do the floor, or the greatest integer, of 40 divided by 2 to the k. And I'm going to raise my powers of k. We start off with k to the 1. So there's our floor of 40 over 2 to the 1. Then we raise our k value up. So it's 40 over 2 squared. And while you're going through these powers, what you want to be thinking is, okay, when do I have to stop? When do I not have to go through adding more terms and raising the power one more? And to do that, think of what, in this case, 40 over 2 squared is. 40 over 2 squared is 10. If you're getting a number that is greater than 1, then you have to move it up 1. I should say, you then have to go on one more term, and you have to raise that power on your prime by 1. Once you start getting terms where what's inside of your square brackets is less than 1, you can stop. So, as we said, 40 over 2 squared is 10. It's more than 1. I need to go up 1 more. 40 over 2 cubed. 2 cubed is 8. 40 over 8 is 5. It's more than 1. Continuing on, adding on 1 more term. 2 to the 4th is 16. 40 over 16 is 2 and some change. So we need to do another term. So 40 over 2 to the 5th. 2 to the 5th is 32. 40 over 32 is 1.25. And you would then write 1 more term. But I know that 2 to the 6th is 64. And 40 over 64 is less than 1. So when I take the floor, or the greatest integer that's less than or equal to 40 over 64, I know that I'm going to get zeros. So 40 over 2 to the 1 is 20. We know that 40, or we know that the floor of 20. Sorry about that. We know that the floor of 20 is going to be 20. That's why we get this term here. We said that 40 over 2 squared was 10, and the floor of 10 is 10. We said that 40 over 2 cubed was 5. So the floor of 5 is 5. 40 over 16, we said was 2 and change. Specifically, it is 2.5. So the largest integer that's less than or equal to 2.5 is 2. So we're just getting these terms down here. And then we said 40 over 2 to the 5th, or 40 over 32, is 1.25. And the floor of that guy is 1. So we add up these 5 numbers, and we get 38. So 38 is the highest power that we can put on 2, and 2 raised to that power will nicely divide 40 factorial. Yeah, it's this is just one more way to say how many 2's do we have in this massively large number that is 40 factorial here. So in the practice problems that will be associated with this video, you'll get the opportunity to do more practice with these guys, but it's nothing really too complicated. It's really just straightforward use of this formula right here. So this is all I really wanted to mention on the greatest integer function, also known as the floor function. In the next video, we're going to talk about another function that is number theoretic, and the function does have a lot of use in number theory, as well as other higher level math courses, including abstract algebra. If you have any questions or comments, be sure to drop them in the comment section below. Otherwise, until the next video, take it easy, guys.